equations. So you just look here, a hose connected to the bottom of the tank, and it is equipped with a nozzle here at the end of the pointing straight up. So that means water is pressurized by the pump and the height of the water jet is just measured. So we need to calculate the minimum pressure rise supplied by the pump. So here, if you read this question, the water level of the tank is 20 meters. So this is the tank. We just redraw it here. So let's say this is the tank, 20 meter. On this surface, we can say this is the free surface, right? And the hose is connected at the bottom. We have a nozzle and it is pointed to the straight point. So you all know that if we use the nozzle, then it will maximize the velocity. So that means we'll get a water jet like this, and the water will go straight up, and after a certain height, a certain elevation, it will just come to the downward directions. So initially the height was 20 meter, and when you're using this nozzle, it can, let's say, travel up to maximum 27 meter. Right, so in the line leading from the tank to the nozzle is a pump which increase the pressure of the water. If the water jet rises 27 meter, that what we discussed earlier, we need to determine the minimum pressure rise supplied by the pump to the water line. So we need to calculate the minimum pressure rise supplied by the pump. Okay, so when we'll try to solve these questions, we are going to use the energy equations for this case, because okay, we'll discuss that later on. So let's say this is point on this point, and this is the maximum height, maximum elevation. This is point 2. Okay, so before going to solve these questions, we'll say this is a steady flow problem and incompressible. Okay, we are not going to consider any friction between the water and the air, also the friction in the hose. Okay, and definitely this is free to the water surface, so that's the atmospheric pressure. So now we know from energy equations, when we discussed the energy equations during the lecture, and when we have 2 points, point 1 and point 2, so we can write it as P on rho g alpha 1 V on square 2g Z1 and the pump head. Okay, it is equal P2 rho g alpha 2 V2 square 2g plus the turbine head plus the Hazel, the head loss. Okay, so that we know, we derived these equations during the lecture. In this case, we are solving it for this point 1 and this point 2. This point on this is actually the free surface of the water tank. Right, this is the free surface of the water tank, and the point 2, this is also the top of the this water jet. That means the water trajectory. And here we all know the velocity of this water. Initially the velocity, we have the velocity of the water, but at this point this water velocity v2 is 0, and as it is just open to the atmosphere, we can say the P2, it is actually it is equal, we can say this is the atmospheric pressure. Here the P on, this is also the atmospheric pressure. So we can say P on P2, this is actually the atmospheric pressure, and velocity of the water at the top of this point 2, this is also 0. Right, so think about the elevations. This point, this is Z1. I can use different color. This is Z1. At this point, this is Z2. We're talking about from here. So this Z1, it is 20 millimeter. Z1, 20 meter. It is given. Z2, this is equal 27 meter. right? So if pressure P1 and P2 equal atmospheric pressure, can we cancel out this pressure P1 and P2? We can. Yes. In this question, we are not using any turbine. So the head loss, the turbine head, this is, we can cancel out this term because it is actually 0 here, because we do not have this mechanical device for this problem. We have the pump, so yeah, we'll get the pump head. Now we said the velocity v2 at this 2.0, so this term is 0. If v2 equals 0, then the whole term it will be 0, right? So now we have the pump head. Okay, we know the j1, we know the j2. Okay, okay, I should write it down here, p2 rho 2, we should have j2 as well. Yeah. So what is v1? v1, it is, you can remember, this is the point, this is the point 1, so, and this is the free surface. So at the top surface, okay, so the fluid velocity at the free surface of this tank, this should be very low velocity. At this point, the velocity v1, it is not 0, but it is very low. So we'll say this is very close to 0, so we'll ignore this term, ignore this velocity. So let's say we'll just ignore this velocity here, because this is very low compared to the, it is just on top of the tank, which is the free surface. So, and the energy equations for a steady compressible flow through the control volume, we always when we do this sort of analysis, we usually use some assumptions. So now this expressions becomes, you see, it becomes j1 plus the pump head, it is equal j2. Okay, we have one more thing, the head loss. Here we will use the head loss as 0, because the question, if you look the question, it says determine the minimum pressure rise supplied with the pump of the water. So to get the minimum value for the required pressure rise, we consider there is no head loss, so the head loss is equal to 0. So this is also 0, so we got j1 plus the pump head, it is equal to j2, or we can say the pump head, it is equal to j2 minus j1, or 27 minus 20, so 7 meter. So that's the pump height we got. So that means the water column height is 7 meter, corresponds to a pressure rise. So we need to calculate the the minimum pressure rise for this pump height. Okay, so we know the pressure rise, that means here the pressure rise, we discussed the formula earlier, so we can write the delta P, that means the pressure change of the pump. So we're going to calculate the minimum pressure. It is actually the rho G and the pump head. Okay, the pump head. So the rho is 1000 for water, this is 9.8, and the pump head is 7 meter. So you can convert it into 1 Newton equal 1000 kg meter per second square. So then if we solve this, then it will be 68.7 kilonewton per meter square, or you can say 68.7 kPa. You know Newton per meter square, it is equal Pascal. So that means this pump must supply a minimum pressure of 78.7 kPa, and yeah, so that's the solutions. So we solve these questions where this is the minimum value, and it should be in reality, the larger pressure rise will need to be supplied to overcome the frictions. We didn't consider the frictional loss here. We made a lot of assumptions to solve these questions. So this is, the minimum pressure that what we need to overcome the frictions. So if we quickly do a review, it is the energy equations, and we actually use the assumptions. Okay, P1, P2, it is atmospheric pressure. We consider this velocity V1, it is negligible, it's very small in fact, so we didn't consider this. V2, it is definitely zero here. We have no turbine here, so turbine head zero. We considered the head loss zero because we actually wanted to get the minimum value for the required pressure, and the yeah, so that's all about. And then we actually got this term, like the pump head is equal 7 meter. So now we calculated the pressure rise corresponding to this pump head. We use the formula like the pump delta P equal rho G into height. This is actually the pump head here. Yeah, so this is the pump.